The next topic we want to cover is that of free energy, delta G. Recall earlier that the total energy, internal energy, was equal to heat energy plus work energy. If we make some assumptions with that equation, such as constant pressure and other things, it will reduce to a very similar analogous equation below, and that is delta G equal delta H minus T delta S. That is the equation that we're going to be using in this class. That is the primary form of total energy that's used in most chemistry textbooks. So let's work through these. Delta G is referred to as the Gibbs free energy. For practical purposes, you can just assume that that's the total energy of a system. Delta H, it's known as enthalpy. It's essentially heat at constant pressure. And a good way to remember that it's related to the heat is the H here can be thought of as just meaning heat energy, but it's formally called enthalpy. And the third thermodynamic parameter we want to look at is this one called delta S. That is known as entropy. And it has to do with the work term. Now, energy, delta S itself, entropy, is a thermodynamic parameter, but it itself has to be multiplied by T before it becomes part of an energy term. So, let's recast delta G as total energy is equal to heat energy minus the work energy. And there we have it, a very familiar equation. Thermodynamic parameters. The three thermodynamic parameters are delta G, delta H, delta S. Again, an energy term, an energy term, an energy term once it's multiplied by T. Let's see how useful that could be in terms of energy diagrams. Let's say, for example, we have a system that we're going to react, and that our reactants, in this case A and B, is, let's just say it's 50 kilojoules. Well, what happens if we can lower the energy of that system? Let's say that we do the reaction and A plus B goes to C plus 2D. And now when I add up all of the energy in C plus 2D, I find out it's less than A plus B. This would be what's referred to as a spontaneous change. This will occur naturally. Think about it as being a ball rolling down a hill. A ball will naturally roll down a hill. And a chemical reaction will naturally go from a higher energy state to a lower energy state. And that's one thing that bears remembering. As a general rule, Mother Nature wants to minimize energy. That's why water flows downhill, and that's why balls naturally roll downhill. Because the water at the bottom of the hill has less energy than the water at the top of the hill. And the same for the ball. And the same for chemical reactions. And so when we go from reactants that are higher energy to products that are lower energy, we say that that's spontaneous. Sometimes the word favorable is used. But how does this look mathematically? And so in this case, delta G is negative. It has to be mathematically. If we take a final number that is smaller than the initial number, a smaller number minus a larger number has to mathematically give you a negative number. And so here we have it. We've got a word that represents the downhill, spontaneous. Another one, we say that's favorable. And we say mathematically that delta G is negative. All three of these say the same thing. Well, let's look at, we have A plus B, and it goes to, let's say, 2E plus 3F, but it's uphill. The total energy in the products is more than the reactants. That reaction is not going to naturally occur. Why? Because it's uphill. It'll no more naturally occur than a ball will roll uphill. Now the question becomes, can you get a ball to roll uphill? Absolutely. You have to put energy into it. You have to make it happen. In other words, that reaction is non-spontaneous, meaning it does not happen on its own. Mathematically, we can see delta G is positive. If you take a larger number, the final state, minus a smaller number, the initial state, the final result has to be a positive number. And so delta G is positive. And we say that is unfavorable. What do we mean? It's unfavorable for it to occur naturally on its own. So here's the punchline of this. If delta G is negative, then the reaction proceeds in the downhill reaction. And the energy flow is from higher to lower. And so we say that's spontaneous. Now, this is of critical importance when we go to making chemical reactions, or we're looking at certain chemical changes and processes. If we can determine if delta G is negative or not, then we have a very good handle on whether energy is working for us or against us. Now, we mentioned delta S. We see from the first slide the total energy is equal to heat energy, and it's minus a work term. Well, I mentioned delta S in entropy, but I didn't really tell you what it was. And entropy is a pretty tough concept. It's abstract, but we're going to look at it on a very superficial level. Now, the reason you may not have heard of entropy before is because it is a bit of a sticky wicket, and normally high schools and some intro chem classes stay away from it. But it's not that hard to understand on a very practical basis. And just understanding it on a very superficial level is pretty valuable in understanding how chemistry works. So let's take a crack at this. So what is entropy? Entropy is essentially a measure of disorder, and that's the key. Disorder. Disorder. As I work through problems, I begin to think of what other words could I use for disorder that would allow me to see what the question is getting at. And so I came up with a list, and I'll give them to you here. And that will give you a good feel, really, a good starting sense for what entropy is. Entropy is a measure of disorder, or randomness, or things becoming more free, things becoming more chaotic and less structured, things tending to run down, energy being dispersed instead of concentrated, right? The conversion of usable energy to unusable energy. So it's this idea of things becoming more and more random and less usable. And that's really what entropy is. Now, we know it's given the symbol S, and we know it has to be combined with temperature for it to actually become an energy term. And so what I'm going to do later is I'm going to refer to this with the negative sign. Is I'm going to refer to this as the work term, or maybe the entropy term. Remember, this is entropy, but it's this entire portion, this entropy term, that helps us determine the sign of delta G, which we'll discuss momentarily. Okay, now that you have an idea of what heat is, and now that you have an idea of what entropy is, so we can now begin to understand delta G. Delta G, what's going to drive that? Well, we want heat energy to become lower. Now, if heat energy becomes lower, if it's downhill, what's the name for that? Exothermic. So we know if a reaction is exothermic, that is favorable or good for delta G becoming more negative. What else do we want? We want heat to be exothermic. What do we want entropy to be? We want entropy to be positive. Oh, by the way, if it's exothermic and heat is given off, you have a smaller number minus a larger number. That means what? Delta H is negative. So let's look at the math. What's favorable to delta G? If delta H is negative mathematically, or if we use the word exothermic, those are the same thing. There's your math speak, and there's your word speak for the same concept. So if it's exothermic or minus, that's favorable to delta G being more negative. Well, no kidding. If delta G is the addition of these two terms, if it's the addition of those two, as this term becomes more negative, this is going to become more negative. So we say delta H being exothermic or negative, we call that favorable. Favorable to what? Favorable to delta G becoming negative. Well, how about delta S? What do we want it to be? We want delta S, on the other hand, to be positive. Mother Nature naturally tries to make things disordered, more random. She naturally converts energy from usable to unusable. She disperses energy. So that's the natural tendency. So, but note, mathematically, if delta S is positive, that doesn't work against delta G, but because once you multiply it by a negative T, a positive number times a negative number becomes what? A negative number. And so now so the more positive that is, the more negative this term's going to be, the more negative delta G. Common sense-wise, what do we say? We want things to get more random, and we want things to give off heat. That's the punchline. More random and giving off heat. More random, and you want to give off heat. Those are the two things we're going to remember that drives a chemical reaction. Oh, well, what if it gives off heat, but it's more ordered instead of random? Oh, well, we'll talk about that in a little bit. What if these two terms work against each other? Well, we'll look at that. But for now, let's continue on and let's see what we have here. So let me kind of summarize or state this favorable and unfavorable stuff in a different cast. So what do we mean by favorable again? Well, it's whatever helps make delta G more negative. It's whatever contributes to our reaction or chemical change or physical change, whatever we're doing, whatever makes it downhill. So we're trying to anticipate what Mother Nature is going to do with things. And if we can do some calculations and find out delta G's minus, then we now know if what we're trying to do is going to be easy, it's favorable, it's naturally, or it's going to be difficult. It's an uphill ride and we're going to have to add energy or something to it. Gives us a great indication of where we are. But right now we're not looking at this quantitative, we're just looking at it qualitatively. So we just agreed delta G, if that's minus, that's a favorable. If delta S is negative, if it's exothermic, that's favorable. If delta S becomes more disordered, that's favorable. This is what Mother Nature tends to want to do. And if she does those two things, this will be the consequence. That's the punchline. Well, what's unfavorable? Well, delta G plus. So you can actually think about the minus sign as being the way I like to think about it. That minus sign means it's downhill. And that's why everything we do centers on this. This tends to be the epicenter. That's it. So we're going to do some calculations or some logic games in a minute. And the whole goal is getting to the question, is delta G minus or not? That tells us if it's spontaneous. Okay, well, what's unfavorable then? Let's take a look at unfavorable here. So what do we have there? Well, of course, if delta G is positive, that means it's uphill. Well, that's not spontaneous. That's not favorable. Right. So what factors from delta H and delta S are going to make it uphill? Well, if delta H is positive, that's going to make delta G more positive. As this becomes more positive, that becomes more positive, so that's unfavorable. Or if what? If delta S becomes negative, if you get ordering, if it becomes more ordered, delta S is negative. Remember, delta S is a measure of disorder. Positive means it's more disordered, so negative means it's more ordered. Mother Nature doesn't tend to naturally order things. If you've got a pile of bricks and you come back 1,000 years later, they're just going to be a pile of torn up bricks. They're not going to stack themselves. But guess what? If you've got the bricks all lined up really nice and you've made a nice castle out of it, and you go away and you leave it for 1,000 years, guess what's going to happen? It's going to go this way. Mother Nature will naturally take things from an ordered state to a disordered state. She's not naturally going to take it from a disordered state to a natural state. That castle is not going to build itself. Why? Because that's uphill. Can you build a castle? Absolutely, but what do you got to do? Put labor and work into it. Now, to get it to tear up, that's no problem. That's spontaneous. This, it's a downhill ride going from here to here, so that will occur spontaneously. You can see the problem with entropy now in the real world. If Mother Nature's tending to make things disordered, that's kind of a bad thing. That means most of what we have is going to wear out and tear up and all of this stuff. And that's indeed true. As a matter of fact, on a somewhat pessimistic note here, ashes to ashes, dust to dust. Guess what? Mother Nature is going to take our nice, structured, ordered bodies that we have all these organs and everything that's functioning in unbelievable coordination to form a living being. And then someday we die and all that stuff's still put together. But then as time goes on in the grave, it's just going to degrade more and more until finally, guess what? People and everybody, we're just going back to individual atoms and elements, only to be used again. Ashes to ashes, dust to dust. Why? Because Mother Nature has a positive entropy. She's going to try to take everything back to basic elements. That's her goal, and we fight it day to day. That's why when you paint something, the paint wears out. It doesn't get better because Mother Nature is working to make everything she can disordered. That is nature's tendency. So how do we look at that mathematically? If entropy is negative and this T is negative, a negative times a negative is a positive number, which is unfavorable to delta G. So at the risk of beating a dead horse, let's look at that one more time where I put the symbols with the words. And you can see there's only 4 possible scenarios. If delta H is minus, that's favorable. If delta S is positive, that's favorable. And a favorable plus a favorable has to give you a favorable result. That's it. A negative number plus a negative number has to give you a negative number. Likewise, if delta S is unfavorable, things get more ordered, and delta H is unfavorable, it's endothermic, delta G has to be mathematically uphill. Well, let's look at another scenario here. Let's look at the scenario in which one of is favorable and the other is unfavorable. Well, what's it going to be? What's delta G going to be? Favorable, unfavorable? We don't know. It depends on which is biggest. If your favorable term is larger than your unfavorable term, then it's going to be favorable on the whole. On the other hand, if your unfavorable term is larger than your favorable term, then the overall reaction is going to be unfavorable. And so that's that scenario where these are working against you. The delta S term, not delta S, but the delta S term and delta H are working against each other. Whichever one's bigger is what the answer is going to be. Similarly, we could look at the same thing here for a situation in which delta H is unfavorable and delta S is favorable. What's the answer going to be if they're working against each other? It just depends on which is larger. If the unfavorable term is larger than the favorable term, it's going to be unfavorable, delta G. On the other hand, if the favorable term is more dominant, larger than the unfavorable term, then it's going to be favorable. Those are your only possible 4 scenarios. And I would probably understand and know how to work those. Because, how to rationalize those. Okay, now I want to take a side, now that we understand overall about this being favorable or unfavorable, each of these components contributing to it, I want to just look at phase changes and revisit something you learned about way early in the semester. And that is, we know that solids can go to liquids and liquids can go to gases. And we learned the names of each of those, right? We've got melting and we've got vaporization and we've got sublimation. So we learned the names of those. Well, I want to revisit that and just put that in the context of thermodynamics. In its natural state, ice is not going to go to a liquid. Let's say if you're below freezing. You're going to have to add heat to it. You're going to have to put some heat on it. You're going to have to do some work on it. So what that means is that this transition is unfavorable. Delta H is positive. You're going to have to add heat. It's an uphill ride. If you want ice that's in your freezer to melt, it's an uphill ride. You're going to have to add some energy there. Likewise, take a cup of water at room temperature. It doesn't naturally go into the vapor phase. You have to do what? Add heat. So it's endothermic in going from liquid to a gas. And the same is true in going from a solid to a gas. So if you look at this little triangle that I told you earlier, solid, liquid, gas, if you draw the arrows kind of in the up direction, those 3 transitions, those 3 phase changes are all endothermic. They require heat to be added to make them happen. In short, going from a solid to a liquid and a liquid to a gas, those changes are endothermic. Delta H is positive for these changes. Heat has to be added to make them occur. Well, by extension, the corollary to that would be going from a gas to a liquid, or going from a liquid to a solid, or going from a gas to a solid. Those are all exothermic. Well, that makes sense. If you want liquid to go to a solid, what are you going to have to do? You're going to have to remove heat. You're going to have to remove heat from that system. When you remove heat, that's called exothermic. And delta H, mathematically, delta H is negative for those. If you want to condense a gas back to a liquid, what do you have to do? You've got to remove some of the energy. And so that's how you rationalize that. So this is important to know for phase changes. Now let's talk about the bottle of perfume problem. Recall, entropy is a measure of disorder and randomness and chaos. And you know that naturally things tend toward disorder. We tend toward disorder. That's kind of common sense. Thermodynamically, we would say we tend toward increasing the entropy of a system. Or put another way, if delta S is positive, then that's what is indicative of a spontaneous process or reaction. So let's look at our perfume dilemma. So we have a bottle of perfume and we take the top off and you smell it. But do you really? And the reason I ask that is that how could you smell it? Because you see, it's in the liquid phase, and for you to be able to smell it way over here, yes, it's going to have to jump out of the liquid and go into the gas phase so that it could go across space and hit you in the nose. But guess what? This is an unfavorable condition here. This is unfavorable. It's not spontaneous. It shouldn't occur on its own. Because I'm not adding heat to this. All I'm doing is taking the top. I'm not adding any heat. And yet you know you do smell the perfume. What's the answer to our dilemma? Our delta H says, our endothermic, our heat term says this should not happen. And yet you know that it does. What's the answer? It lay in the fact that we were just considering delta H. But as you know by now, there is much, much more to the story. What is it that controls a reaction? Delta G, not delta H. And it's true for our perfume bottle. It's absolutely true. Delta H was indeed unfavorable. You know that there's more to the story. The heat part is only the half. What's the other half? The entropy term. So let's think about that. If this is unfavorable, then for this to actually be favorable, this must be really favorable. Is it? Well, let's see if we can rationalize it. All of the molecules are stuck in this little bottle, and when we take the cap off, they have more freedom, and they have more freedom, and they have more freedom. And they can go anywhere they want in the room. Whereas once they were confined to the bottle, now those molecules can go everywhere. So the increase in entropy is absolutely tremendous. So even though it's true, you had an unfavorable enthalpy term, unfavorable heat term, you had a very favorable entropy term. And so what perfume really is an example of? This scenario number 4. And in this case, the favorable part is much, much greater than the unfavorable part. And so delta G is negative, and the process is overall favorable. It's spontaneous in nature, and indeed you're correct. You do smell it, despite the fact that your heat term is working against you. Your entropy term is really working for you even more, and that winds up making this a favorable transition. And that's the story of perfume, and that's where we're going to end it here.